Hello everyone and welcome back to Reversing with IDA Pro series. In this and next few videos, we'll analyze a very interesting sample which represents one of the layers of TorLocker ransomware. You might have heard about TorLocker from the news. In these videos, we'll see an overview of what's happening under the hood. Please be very careful and only run it on an isolated virtual machine. In this first part, we'll see a way to statically analyze memory blocks decrypted dynamically in memory. As usual, we'll open the sample in IDA Pro. It's an x86p file, although we don't have an extension. We begin the analysis from the start function. One of the very first blocks here allocates memory dynamically using virtual alloc function. The return address of the block is moved from EAX to EDI register. What happens with that memory block? A number of bytes specified by ECX counter get copied there from ESI. ECX register contains actually the number of bytes dynamically allocated by virtual alloc. The copy is done using the repmove SB instruction byte by byte from the block pointed by ESI. To see the data source, we need to follow the ESI pointer, which goes into data section. This looks like random bytes. Nothing interesting so far. Let's go back to the code and run the sample inside the debugger. First, set up a breakpoint near the virtual alloc call. Run the sample, accept the warning, and stop at the breakpoint. We'll tidy up the debugging interface a bit to make sure all the useful windows are accessible. Okay, as a tip, you can actually save the Windows layout by going to Windows menu, Save Desktop. Looks nicer now. We'll use the hex view later to track memory block similarly with Immunity Debugger. Good. On the right side, we see the evolution of all the registers. EDI and ESI were of interest to us. Right, advance a few instructions and notice how the address of the new memory block gets stored into EDI. There. Okay, we copy the value of EDI. We will inspect it later and see what gets copied there. We advance a few more instructions until we get past the repmove SB instruction, which is responsible for copying the block. To navigate in the hex window to a different address, simply press G and then type the address. These are actually the gibberish bytes we've seen before in the data section. The purpose of this copy procedure will become clear later, but it's not relevant to our goal in this video. The next function receives, as one of the parameters, the pointer to data section, which is possibly encrypted. The other parameter is a pointer to a strange block of random bytes. We don't know yet, but this is actually the key used to decrypt the initial bytes in the data section. It will become clear in a second how. We will see together. Let's rename the function as decrypt data section. Good. Okay, let's see what happens. check the source bytes before the call. After the call, we now have instead readable ASCII values. Remember, we can quickly convert those from data bytes to ASCII strings using the A shortcut key. Further down, we have an interesting URL location, probably a second stage payload. Very nice. We've convinced the sample to decrypt the data section dynamically. The problem is that if we close the debugging session, we lose access to all those values decrypted dynamically. So, let's terminate the debugging, then check again the address that contained data which was decrypted. Back to encrypted form, unfortunately. Even if we save the database and we close IDA Pro, the decrypted values won't be retained. Let's reopen IDA and let's see. Still encrypted. We need to find a way to keep the decrypted data section and be able to reference it during static analysis. Turns out, this is actually very simple once we understand what we're trying to achieve. First, run the debugging session again and continue until the data section is decrypted. Okay, now it's decrypted. At this point, take a snapshot of the memory of the process memory. Go to Debugger menu, take Memory Snapshot. We have two options. We can save all the segments or only loader segments. For now, select just loader segments and we'll talk about the difference between the two options later. Stop the debugging and go to the code. Notice that now all the ASCII strings are decrypted. Exactly what we wanted. Let's see if they persist after we save the IDA database and reload the analysis. Great! Data section is still decrypted. Alright. One more thing. What is the difference between loader segments and all segments options? Step through the code, go past the dynamic allocation function call, then go to the segments subview. View menu, open subviews, segments, or simply Shift plus F7. The code allocated one block dynamically here, and we have a bunch of other blocks also allocated dynamically. All the ones starting with debug are allocated at runtime and are present only during the debugging session. If we take a memory snapshot only with loader segments, these debugging blocks would be lost. If we care about those blocks, we need to use the all segments option instead. Clear now? In our case, it doesn't matter because the decrypted bytes were actually located in the data section. Alright. Check the name of the segment here. In the next video, we will deep dive into the same sample and see another way to deal with blocks decrypted dynamically in memory. Thank you very much for taking your time to watch this. As always, make sure to play with the sample on your own. See you later.